Hi! By now we have seen many different aspects of linear algebra, both analytical and geometrical. It turns out that asking questions about linear transformations based on geometry will lead us to interesting and important conclusions. So let's continue this project here. Suppose we start with a unit circle and apply a linear transformation with standard matrix A. Then we will obtain an ellipse. But what ellipse exactly? What are the lengths of its semi-major and semi-minor axes? To find this out, it will be useful to consider the eigenvectors of the matrix A. As you can see, they end up on these semi-major and semi-minor axes touching the ellipse. This means that the lengths of these axes are equal to the absolute values of the maximal and minimal eigenvalues, respectively. Indeed, we need the absolute values since, for instance in this case on the slide, the minimal eigenvalue is negative. Great! Now let's try something a little bit more complicated. Instead of a unit circle, we'll start with a unit sphere. When we then apply the linear transformation with standard matrix A, we obtain again an ellipse, but this time also the interior points. One way to think about this is that the linear transformation represents the casting of a shadow. Again, we are interested in exactly what ellipse we are looking at here. In particular, we want to know the lengths of the semi-major and semi-minor axes. Luckily, we already know what to do. We simply need to compute the minimal and maximal eigenvalues of A. So we'll start by subtracting lambda times the identity matrix. This gives us... Of course, we need to subtract the 3x3 identity matrix this time. Again, a no-go, of course. This is because only square matrices have eigenvalues. It seems we need a slightly different concept to answer the same question for this non-square matrix A. So let's go back to our original problem. We start with the unit sphere, which is given by all vectors of length 1. To find the length of the semi-major axis, we actually want to find the maximum length of a vector on the sphere after applying A. So in fact, we are looking at a constraint optimization problem. We are trying to maximize the norm of A times x under the constraint that x be of length 1. Of course, we may as well maximize the norm of A times x squared, since if the norm of A times x is maximal, then so is its square. It helps to go to the square because we want to somehow look at a quadratic form. We've now gotten there since the norm of A times x squared equals the dot product of A times x with itself. This equals x transpose times A transpose times A times x by the relation between the dot product and the transpose. So we are looking at an optimization problem of the quadratic form given by the symmetric matrix A transpose times A. We know then that the maximum is given by the maximum eigenvalue of A transpose times A. So what does this say about our problem? Since the length of the semi-major axis was given by the maximal length of A times x, not squared, this would be the square root of this maximal eigenvalue. Note that this is the maximal eigenvalue of the matrix A transpose A, which is always a square matrix. Now how about the semi-minor axis? Of course, it is not the minimum of the norm of A times x with the constraint that the norm of x is 1. Indeed, the interior of the ellipse is in the image, and so the minimum length of A times x is simply 0. Instead, we are actually still maximizing, but simply with an additional constraint. Indeed, now we have not just that the constraint that the norm of x is equal to 1, but also that the image vector ax is orthogonal to the semi-major axis. So that if u max is the eigenvector of A transpose times A corresponding to the maximal eigenvalue, then we want the additional constraint that u max dot x is equal to 0. This constraint optimization yields simply the eigenvector corresponding to the second largest eigenvalue of A transpose times A. So similarly to the semi-major case, we see that the length of the semi-minor axis is given by the square root of the second largest eigenvalue of A transpose times A. Of course, the minimal eigenvalue is 0 in this case. Here's a good example of how simple geometrical questions can result in apparently interesting quantities. In this case, the square roots of eigenvalues of A transpose times A for any matrix A. So what exactly is going on here? What are these values, and in what generality can we apply this method? Considering the generality is a good starting question, whether we can always take square roots of eigenvalues of A transpose times A. It turns out that indeed we can, since the eigenvalues of A transpose A are non-negative for any matrix A. The proof is actually quite simple, since if lambda is an eigenvalue corresponding to a vector v of length 1, then lambda equals v transpose times lambda times v. This in turn equals v transpose times A transpose times A times v, since v is an eigenvector with eigenvalue lambda. Of course, this is simply the dot product of A times v with itself, which is the norm of A times v squared, which, being a quantity squared, must be non-negative. So we can always take the square root of all eigenvalues of A transpose A. As we have seen, these numbers have interesting qualities, and so we will give them a special name. The singular values of a matrix A are the square roots of the eigenvalues of A transpose A. We usually denote them sigma 1, sigma 2, etc., and order them from largest to smallest. We also include multiplicities, meaning that if an eigenvalue has a multiplicity of 3, for instance, then the square root of that eigenvalue will occur 3 times as a singular value. So with this terminology, the answer to our filled ellipse question becomes that the length of the semi-major axis is given by sigma 1, the first singular value, and the length of the semi-minor axis is given by sigma 2, the second singular value. It turns out that these quantities have very important applications in what is called principal component analysis, which we will say something about later. An important mathematical input for this principal component analysis comes from the so-called singular value decomposition. This idea is most easily explained by considering what we do with eigenvalues. Indeed, one great thing about eigenvalues is that we can use them to diagonalize. So perhaps we can do something similar with singular values. This will be the topic of the next lesson.